So we'll finish what is this one? August 2015 exam, Common Core Geometry, and we kick it off right here with what could be a pretty tricky problem. What we'll do is we'll start by graphing, sorry about that, we'll start by graphing the coordinates we do have. So -3, -1 is B, and we have C at -1, -4. Okay, so there we are. Now, what does this mean? A is somewhere along the line, y equals 3. Okay, we don't know exactly where. But what I'll do is I'll sketch that. Okay, we know A has to hit somewhere along this line, y equals 3. It's a horizontal line. Now, we need to make triangle ABC a right triangle and justify it. Okay, so this is a lot, but it is a 4-point question. So let's get started with that. Obviously, for a right triangle, we're going to need a right angle. And when we have, the analytic proofs or analytic problems with coordinates, you're probably going to want to show that slopes are negative reciprocals. That's going to get us perpendicular, and perpendicular gets us right angles. Okay, so that's kind of got to be our goal. Now, which angle is going to be the right angle? Well, it could be, in fact, it could be A, but I'm going to prove in a minute that that's going to be a possibility that can't happen just by the sheer distance of how far this is away from those 2 points. If angle B is the right angle, yeah, we can do that, and same with angle C. What I'm going to start with is the idea of, let's get the slope of BC. Because that's how we're going to do this. So we'll start with that. It is, I don't know, however your teacher shows you this. I like, if we can graph it, I like doing rise over run. Some teachers prefer this formula, y2 minus y1 over x2 minus x1. So that's the algebraic way. I simply do rise, the 3, over the run 2. And since we always move left to right to read a graph, just like a book. And if I'm reading this left to right, it's going down, so I'm going to throw a negative on there. So a perpendicular line will need the slope to be positive 2/3. That is your negative reciprocal. Now remember, we're shooting for 4 points. We want to really justify what we're doing the whole way, okay? Justify the whole way. And you don't want to leave any room for, somebody to score it less than 4 points. So that's why we're doing all this. Negative reciprocal slopes give perpendicular. Okay? So we're going to say this. From B, apply a slope of 2/3. Right? That's up to right 3. So let's do that. Up to right 3, up to right 3, up to right 3. Okay, so this, if we went along this line, that would get us a right angle. So one location for A could be 3, 3. So that's one answer. X could be 3. If we go from C, again, do the same thing. Apply a slope of 2/3. Up to right 3, up to right 3, up to right 3, up to right 3. Okay, that's going to hit, it looks to me, wait a minute, I must have miscounted. Up to right 3, up to 1, 2, 3. No, that's right. Okay. It looks like it's going to hit right there. What is that? About 9.5. So X could be 9.5. That's another possible location for A. Now I want to go over to Geometer Sketchpad. Oh, by the way, that would make see the right angle. Okay, I'm going to pick x is 3, makes angle B the right angle. Okay, since triangle, let's do that. Since triangle ABC has a right angle, A at 3, 3 makes triangle ABC a right triangle. All right, now we finished that problem, but I do want to show you something important over here. When we go over to Geometry Sketchpad, let's see, I created that same type of problem. It's not liking this for some reason. Okay, I created that same type of problem here. Let's say we slide it up to there. Maybe not. Okay, let's say that's B and C. Let's label those guys. Label, show labels. Oh boy. Let's change it to B. Okay. Here. All right. Now, what I wanted to teach this, just to make sure that we understood this, was if we have a circle, go back over to this because I can sketch that. One of the theorems that we do need to know is that if we have a circle and let's say diameter BC, right? Now, if that's a diameter BC, anywhere, if we place A anywhere on this semicircle, you are forcing this to be a right angle. Okay, that's one of the circle's properties. So I'm going to use that concept over here on Geometry Sketchpad. Okay, if I can get over there. What I'm going to do is I'm going to construct a circle eventually. I'm going to draw that segment. Let's say I found the midpoint. Okay, let's draw a circle around that. You could do this right on the graph. Now I could pick any point up here on this circle, and that's going to get us a right angle. So if this, let's say that were, I call it A. I gotta get this back up. If that were A, we would have ourselves a possibility of A being the right angle. Well, what's the issue, right? This line is too far away. Okay? If this line were closer to BC, we have options. This line is so far from BC that we cannot let A be the right angle. And that's what's happening over here. Okay? If you found the middle of this and drew your circle, okay, let's say we draw a circle. All right, A would have to be somewhere on this circle, and it'll get nowhere near that line. So that's why A cannot be the right angle. Just an important thing to consider in case they do this problem again, and give us another option. Okay, next one. Great. This is a different type of proof. This is not your synthetic proof. This is using rigid motion transformations. Okay. All right. So let triangle DEF be the image of D after a translation along L, such that D is mapped to A. Okay. Oh, where's F prime going to be? F prime is going to land on C. Explain your answer. Explain your answer. Collinear. Okay. All right. What I could say is the translation. All right. So yeah, we have, here's what we'll do. There's probably quicker ways to do this, but we've got to make sure that we show why does F land on C. Okay. Um, so f prime, sorry, f prime is C. That's what we want to show. All right, f prime is going to be at C. All right, let's go through this. So, since D mapped to A after the translation, the translation vector has a magnitude or a distance of CD plus CA. All right, why is that? All right, because CD plus CA equals DA. And that's, you could use segment addition postulate. Right? So that gets us your magnitude or your distance. All right. Now, every point in a translation moves the same distance. Okay? Now, here's what I'm going to show. I'm going to show that FD, the FC is the same distance. So, here's what FD equals. Or FC, I mean. FD, whoops, you don't want to borrow about that, plus CD equals FC, right? Again, segment addition postulate proves that. All right, let's go through some stuff now. If you notice, in both cases, we have CD. All right, CD is equal to itself by reflexive property. Right? And it's given that CA equals FD. That's given. All right, now we got to piece all that together. All right, this is pretty tricky. I'm certain there's way easier ways to do this, but I want to make sure that, again, it's all about not leaving any points on the table. All right, so let's take this, and these key pieces of information, and we'll get FC equal to DA. All right, so here we go. Let's rewrite CD plus CA equals DA from above. All right, now we're going to manipulate that a little bit. Okay. Let's see, do we have replacements? Yeah, we do. Okay, now FD can replace CA. And that's substitution. Okay, now what's CD plus FD equal to? FC. From above, right? What's our conclusion? I'm sorry, DA is equal to FC by substitution again. All right. So basically, I wrote all this. I probably just needed to go right to there, but I didn't want to leave any doubt. All right. Basically, what is this showing? This is showing that this distance, this move from D to A, is the same distance as from F to C. So the translation vector that we use to go from D to A is going to be the same distance as F to C. So we've established that. Okay. So now we'll come over here. Now the translation vector D to A is the same magnitude as F to C. That's 1 point. Now, the other idea is the fact that they're collinear. Okay, so since A, C, D, and F are collinear, from the given, not listening. Okay. Since A, C, D, and F are collinear from the given, the direction of the translation stays on the line L, because that's F, D, C, A, that line. So F prime lands on C. Direction and magnitude are shown. Okay, the direction, meaning when you have a vector, you have to give the direction. That direction that it's going to go is along this line. It's going to stay along this line because they're collinear. The magnitude we showed was the same right here. Okay, so direction and magnitude, that's why it lands there. It's way overboard, but again, it's a 4-pointer. I don't want to leave any doubt here. Let D double prime, okay, be the image. All right. So basically, here's what happened. F landed on C, D landed on A, E's up here, okay? E is parallel to this line, okay, so this is E prime. Now, let's see, the only way, after reflection, suppose E is located at B. Okay, so what we're saying is if E double prime does land on B, all right, they must be congruent. Here's why. Basically, let's see, let's talk about this. After the line reflection, over line L, points, what are they, D and, no, yeah, D prime's here, and F prime's there. So D prime and F prime remain invariant because they are on, don't move, because they are on of reflection. Okay. Need some more room. Now, this is getting to be bad, but we got to make sure we cover all our bases here. Now, since the line reflection maps, what is it? E prime onto B, this gives us a sequence of rigid motion transformations that map. Okay, now this gets tricky. F to C. What else? D to A. And it looks like E to B, right? Yeah, E to B. So that's good. Let's come over here. 3 points in a plane that are mapped to each other. 3 non-collinear points. Right? Because that's what these are. F, D, and E are non-collinear points that are mapped. 3 points in a plane that are mapped to their corresponding points using rigid motion transformations. Will produce an image that is congruent to its pre-image. So, therefore, triangle oh, there we are. Sorry, I went too far up. I'm looking for the, what am I trying to prove again? So then, therefore, triangle DEF is going to be congruent to triangle ABC. So that was overboard, but that covers everything that's key on this. Now, we didn't map angles or sides. That's why I have to say something along these lines, okay? So we didn't have like side angle or anything like that. So you got to be careful with that, how we produce the congruent figures. And that was pretty tricky. All right, next one, prove it's a rhombus. So I need all the sides the same, if I remember this one correctly. Need all the sides the same. So how are we going to get it? So CE is the same as CF. Whoops, wrong one, right there. And ABCD is a parallelogram. So what I tend to do is pull this apart, okay, one step at a time. It's a parallelogram first, that's what's given. So what do I have? Well, I've got this whole side. Let's see. Will that help me? Let's see here. Oh, yeah. So this side's equal to that one. This side's congruent to that one. Let's see. Is parallel going to help us here? What if we got these two triangles the same? Yeah, that might do it. If we can get these two triangles, see this one? If I can get these two triangles the same, let's pull those out. So you got the side BC to E. We've got to somehow get those the same. All right, then we've got F to C to D. F to C to D. Now they gave us what? These two the same. Perpendicular, I missed that. That's what they've given us. BE is perpendicular to CED. So EE, there we go. Get that right angle. And DF perpendicular to DF. Okay, so that's going to get us a right angle there too, but that's only two pairs of course. Oh, geez. I missed this. So simple. Reflexive property right there. Okay. So we'll need this parallelogram idea, but we won't. I don't think we need to start off with that. Let's get rid of that for a minute, just to give our. No, I'll just make some more room. All right, let's get going on it. So first, I'm going to get the triangles congruent, and let's start with that. Step one, I'm going to say it's going to be an angle side angle proof. Okay, let's just go with angle C is congruent to angle C by reflexive property. Then 2, so that's one pair of angles. This was pretty easy. They gave us this, so why not use it? It's by given. All right, 3. Now we're going to work a little bit for that other pair of angles. Let's use the perpendicular. So BE is perpendicular to CED. And we'll do this at the same time. BDF perpendicular to BFC. And it's by given again. Now let's do something with it. This is the first time we're going to do something on our own. Let's go with B. We already got that. We don't need the D, but what we're going to have is angle, and use a 3-letter path here because there's really 2 E's. So we're going to say angle B, EC, and angle. Let's get this correct. It looks like D should match, right? DFC. First, they are right angles. And let's explain that quick. Perpendicular segments form right angles. Create, form, whatever. Now we'll say they're congruent. Because all right angles are congruent. Okay, that gets us the triangles congruent. Let's get some more space though. That'll at least get us most of the way there. So triangle, BEC is congruent to triangle. Whoops, use that triangle symbol there. DEDFC by the angle side angle. Triangle congruence theorem. All right, that gets us out of 6 points. It's going to get us probably 3 or 4. Now we got to go back to the idea of that it's a parallelogram, and then we'll show you how to step it up. So we're going to use ABCD as a parallelogram because it's given. Now this is where it gets a little weird. Okay. Oh, whoops. This was bad order. I should have switched these, but it's not a big deal. 8 is going to be based on 6. Forgot about that. Sorry. BC is going to be the same as CD. BC is congruent to DC. All right, because corresponding angles of congruent triangles are congruent. It's kind of out of order. I should have had 8 and 7, should have switched, but it's not going to be the biggest deal in the world there. You know, I should have swapped these two just for nice ordering, but it doesn't make any difference. Okay, now I can say ABCD is a rhombus. And the explanation here is that because a parallelogram with consecutive sides congruent is a rhombus. And there you go. So what am I saying there? I'm saying that I've got parallelogram, and then I showed these two sides were the same. So once you show the consecutive sides, the next to each other sides, once you show those are the same and you have a parallelogram, all 4 sides end up being the same, which is a rhombus. All right, last one, the candles problem. Okay. Let's see. 8 inches, 3 inches, volume of the candles. Okay. So that one's pretty straightforward, it looks like. So the height of this figure is what? 8 inches. 3 centimeters across. One candle. One candle, one candle, one candle. All right. So let's start with just the volume of one candle. Shape of a cone. So 1/3 pi r squared h. R is going to be 1.5 centimeters, just because the diameter is 3. Don't forget to square it. And let's get one of those. Looks to be, how much? 18.8496. 18.8496. And that's going to be inches cubed. Okay. So each mold have a height. Okay. Total volume of 100 candles. So 100 of these. Volume is 1885 cubic inches, because I multiply by 100. Okay, that number times 100. All right, that gets that part down. Now, Walter goes to a hobby store. 10 ounce. Okay. All right. This is going to be interesting. So there's a few ways to do this. Let's go with how many ounces we have first. Let's go for how many ounces first. So what we have is, wait a minute, for 100 candles, let's stick with 100 candles. So we have a volume of 1885 cubic inches. We're after the ounces. So let's keep consistency here. I'm going to set up a proportion. There's better ways to do this, but I just like to do it this way to keep it simple for my students. And you read this density, okay? And let's go with ounces have to go across from ounces. So 0.52 ounces for every 1 cubic inch. Okay, so then we're just going to cross multiply. So x equals whatever 0.52 times this 1885 is. So go ahead and hit the calculator on that. It looks like 980.2 something. And that's not it. That's just the ounces. Now, it's ounces. Now we got to get a cost of that. Sorry, cost is next. So we have 980.2 ounces. We want to know the cost in dollars. So we'll call that. We already used X. Let's use Y. Okay. 10 cents per ounce. So let's put 0.10 down there. Right there. So that's your cost for every 1 ounce. And again, so let's cross multiply. And the cost for this is, looks like 98.02. Yeah, 98.02. Sorry about that. Should have been simple. Just move the decimal place. Okay, so the answer to this is the cost of 100 candles. It's going to be $98.02. So that's that part. Let's box this in. 100 of these. Okay, so we got 2 parts answered. There's more. Oh boy. Okay, so he spent $37 on the molds and charges $1.95 profit. Okay, so the total cost, profit is going to be revenue, what you bring in, minus the costs, the total cost. All right, so what's the revenue? It's $1.95 if he sells them all for all. Let's assume he sells all 100. We're going to get that revenue, what you bring in. Now the cost, it's going to be first the 98.02 plus the 37. You got to pay for that molds and all that stuff, right? So the profit's 195 minus whatever that is, 135.85. And your profit's going to be $59.15. So there it is. Very tricky problem. Hopefully this is helpful. Hopefully we get some people to like the channel, and I'll keep them going. Thanks so much.